In this video, I'd like to walk you through a few sample problems. This activity, which is our second lesson in the first part of our unit number 5 in calculus, this activity is asking you to complete just a series of practice problems from the textbook. So the textbook section is 4.9. We're looking at the collection of problems from 11 to 46. But I don't want you to do all of those. I only want you to do the numbers associated with 0 mod 3. Now this is a phrase that we use in something called modular arithmetic, and you can search that on your own for more information if you'd like. But essentially this phrase 0 mod 3, this is implying that I only want you to complete multiples of 3. So instead of just saying do the evens or do the odds, I'm asking you to do multiples of 3. If I were in the future to ask you to do problems associated with 1 mod 3, well that again is in a sense multiples of 3. It's every third problem, but you're starting essentially with the number 1. So 1 and then 4 and then so on. In this case we're starting at 0 and every third problem from there. So 0 mod 3, if I started at 0, which isn't in this list, I would complete it and then go to 3, 6, 9 and so on. So this particular assignment is asking you to do 12, 15, 18, 21, and all other multiples of 3. For this particular video, I'm not going to complete any of those examples, but I'll complete some that are similar. And after I'm done walking through these sample problems, the ones that I've identified in green, I would encourage you to practice more of these as the weeks progress to make sure that you're getting more comfortable with computing the antiderivatives. What you can also do for help, if I'm not available or if you don't get a chance to ask me in class, of course send me a message through Schoology or by email. But also when you log into Math Excel, this is a sample of what your screen would look like when logged in as a student. If you jump down to your study plan and select all chapters, the section 4.9 can be found by expanding chapter 4 and then expanding chapter 9. And if you wanted to practice within here, you can select any one of these groups. I'm actually going to select all of 4.9 so that I can see all practice problems associated with it. Since I'm asking you to complete questions number 11 through 46, well, here you'll find a whole bunch of questions associated with problems 11 and beyond in this section. 11 to 46 is represented through this block here. And you can click on any one of those and complete them like a Math Excel question with the question help and all the other tools that are available. So by doing practice this way, you're not actually completing the problems for credit on Math Excel, but they are available for that extra help if you need it along the way. Okay, so here we go. The instructions simply say to find all antiderivatives of the following functions. Check your work by taking derivatives. So we need to establish the antiderivative and then also check our work by taking the derivative of our result. So let's start with number 11 here. We've got f of x that equals 5x to the 4th power. So I think I'll just copy that down here. If I need to find the antiderivative, the symbols that I would use is the indefinite integral and then the function 5x to the 4th power, and immediately following that function we need to identify the differential. We need to include this dx with it. So with f of x being 5x to the 4th power, we're going to need to take the antiderivative of this function. Now one of the things that I like to do is push any constants to the outside because of that constant multiple rule we discussed in the prior video. So now I'm dealing with 5 times x to the 4th power, 5 times the antiderivative of x to the 4th power. Now the antiderivative of x to the 4th power, that follows our power rule. And our power rule stated that I can increase the exponent by 1 and then immediately divide by the exponent plus 1, which in this case is 5. And we can't forget about the plus c, our unknown constant. And this is what's meant by finding all antiderivatives. If I were to eliminate or not include that c, this is going to be one antiderivative to the original function, but this could be another antiderivative, and this could be another. And since we're not going to list everyone individually, we account for this additional constant value by writing plus c. Now, of course, we can simplify this a little bit. The 5 that multiplies by the fraction x to the 5th over 5 simplifies, of course, to x to the 5th plus c. And I think that's a pretty good antiderivative. To check this, we would take the derivative of x to the 5th power with respect to x, and we'll say x to the 5th power plus c, of course. And the derivative of this power rule, of course, would be 5 times x to the 4th power. The derivative of c is 0, and so here again we see 5x to the 4th power, which is exactly what we started with back here. And so that series of work would be a good way to illustrate a complete result for problem 11. Let's try number 14. So number 14 is g of x equals negative 4 cosine of 4x. So if I need to find the antiderivative, I would use the antiderivative symbol. It's kind of like a scripted S, a little bit more narrow than that. We've got the function, negative 4 cosine 4x, and our differential with respect to dx. Now sometimes we'll put a grouping symbol around the expression, and sometimes we don't. It's really a user preference. I tend to use parentheses only when we've got multiple terms that are separated by addition and subtraction signs. That's just, that's my habit. Now the constant negative 4 can be pushed to the outside, so I'll do that. And now I've got cosine of 4x dx. And I have to think about what function has a derivative that would be equal to cosine. Now I specifically remember that sine will do that for me, but I don't remember what happens when we've got this multiple on the interior. And that's okay, because we did in the last video provide a collection of antiderivatives for trigonometric functions, and I think based on our current situation, I'll probably provide the entire list of integrals for you to reference in this section. Of course, there are some integrals that are easy enough to memorize, but it would be fine, I think, in my opinion, to reference the antiderivatives for these computations from the table in the textbook. And so the table in the textbook is just a more complete list than what we see here. For right now, what I'm looking for is the antiderivative of cosine, which is right here, and it's the antiderivative of cosine with some sort of multiplier on the interior. And so the antiderivative of cosine with a number that multiplies on the interior is 1 over that value, 1 over that multiplier times sine of that internal expression. So we have an antiderivative of 1 over 4 sine of 4x, and we'll add c to the antiderivative. And as I mentioned in the last video, I guess technically speaking, the plus c would be located in here, but there really is no need to multiply or distribute this negative 4 in to call this a 4c or anything like that. The constant, the unknown constant that creates the family of antiderivatives can simply be listed on the exterior one time. Of course, we will clean this up just a little bit. We've got negative 4 times a fourth. Well, that turns into a negative 1, and we now have negative sine of x, so negative sine of, 4x plus c. We expect that to be the solution, and we can test this by finding the derivative with respect to x of negative sine 4x plus c. And this negative sign kind of acts as a constant multiplier, so I'll push that out to the front. The derivative of sine would be cosine, and we have to use the chain rule here because on the interior of that sine function we have a whole nother function that's 4x. So the derivative of the outside is cosine of this argument, and we have to immediately multiply So after we take that cosine, we would immediately multiply by the derivative of the interior, which is 4. And the derivative of c is 0. C is just going to represent any number, some arbitrary constant. And the derivative of a constant we know is 0. If we were to clean this up, we've got a negative sign and a 4 in a series of multiplications, so I'll just reorganize that because of the commutative property of multiplication. And we'll call this negative 4 cosine of 4x. And sure enough, that's what we started with back here, so I'm happy with that as a solution too. And again, this line of work I think would be sufficient for a question like 14. Okay, how about 15? 15 is yours, so let's try number 17, negative 2 over y cubed. And this equation is kind of interesting because it's a function built on the variable y. That's okay, it's just a bit unusual. One thing that I'm probably going to do here is rewrite this function as a product of a variable with a negative exponent. That'll fall in line a little bit better with the antiderivative rules that we've practiced so far. So here we have negative 2 times y to the negative third power. So if I were to take the antiderivative, or find the indefinite integral, we sometimes call it, I need the antiderivative of negative 2 y to the negative third power, this time with respect to y, so dy is our differential. I'll push this negative 2 out front, and we have the antiderivative of y to the negative third power with respect to y. And here again we can use our power rule. So we've got negative 2, and the power rule says to take the exponent and increase it by 1, and then divide by that new exponent, and add to it an arbitrary constant on the exterior. If we were to simplify this a little bit, the negative 2, when multiplied into this fraction, becomes, well, 1. They essentially cancel. And we have now y to the negative second power plus c, or in other words, 1 over y squared plus c. We can check our work by finding the derivative with respect to y of 1 over y squared. Can't forget about that c value. I'm guilty of it too. So 1 over y squared plus c. This would be the same as d over dy of y to the negative second power plus c. That might be more helpful. And of course the rule here says to, when finding the derivative, to bring the coefficient down, negative 2, y, and then decrease the exponent by 1. So we call that negative 3. And the derivative of c is 0. And so the derivative of 1 over y squared is negative 2 divided by y cubed. And this expression, of course, is what we started with. So here again, that line of work, that amount of work, I think would be appropriate to answer a question like number 17. All right, so we've accounted for 11, 14, 17. The next one I want to talk about is number 23. Now this is where we start getting into a combination of functions, but that's okay because we do have a sum and difference rule for antiderivatives. And we're even given the integral in this case too. So the problem actually states the integral of 3x to the 5th power minus 5x to the 9th power with respect to x. So that's how the problem was given to us in the textbook. We can go ahead and work through it from here. Now I'm going to do two steps at once. I'm going to treat these as two separate integrals, and I'm going to move the constant to the front. So I'm going to say that this is 3 times the antiderivative of x to the 5th power with respect to x minus 5 times the antiderivative of x to the 9th power with respect to x. So I split this into two integrals because of the sum property for integrals, and then I also moved the constant multiplier to the front of each as well. So now what we're left with is the result, 3 times, now the antiderivative of x to the 5th is going to be x to the 6th over 6, and the antiderivative of x to the 9th is x to the 10th over 10. And rather than including a c value in each of these antiderivatives, I'll account for that c value at the very end. That's perfectly fine. And we can clean up our results from here. This 3, when multiplied in, creates a fraction 3 over 6, which is 1/2 x to the 6th power. And the 5, when multiplied in, also creates the fraction 1/2. So this appears to be a pretty good antiderivative, or indefinite integral, as our textbook calls it in this case. Both of those terms are essentially synonymous, so we can switch between them. And we are being asked to check our work by using by differentiating, so we'll go ahead and do that here. Now the derivative of 1/2 x to the 6th power, if I bring the 6 down and multiply it by the 1/2, I do end up with 3, and I reduce that exponent by 1. If I multiply the 10 by a negative 1/2, that becomes negative 5x, and we reduce that exponent by 1. And we could take the derivative of c, which of course is 0. And certainly this expression, 3x to the 5th power minus 5x to the 9th power, does match the expression that we started with here. So I'm perfectly fine with this solution for number 23. Okay, so 23 is done. Now let's take a look at 28. I might be able to squeeze it in right here. So in this case, we have a product of two functions. It's like we have a factor in front of a grouping symbol. And there are techniques where we can find the antiderivative of two functions that are multiplied together. We haven't covered them yet in class, and I hope to do so before the end of the semester. But for right now, I think it would be a whole lot easier just to distribute this 5m into both terms. And by doing so, we now have an expression that's almost identical, or at least structurally identical, to a problem in number 23. And so we would approach it much the same way. In fact, if you're becoming comfortable enough with these antiderivatives, or these indefinite integrals, you can probably just jump to a line like this. 60 times m to the 5th power over 5 minus 50 times m to the 3rd power over 3 plus c. And that allows us to skip this step of rewriting the expression. And I'm okay with that, especially in these simpler problems. We should simplify, however. 60 divided by 5 is 12. So we've got 12m to the 5th power. 50 divided by 3, well, that doesn't divide nicely, so I'll leave that as a fraction. 50 thirds m to the 3rd power plus c. And I think that would be a pretty good antiderivative, or indefinite integral, of the original expression. Now, of course, we can check our work by taking the derivative of the expression we just established. 5 times 12 is 60. Reduce the exponent by 1. 3 times 50 thirds is 50. Reduce the exponent by 1. And the derivative of c is 0. And this 60m to the 4th minus 50m squared does match what we have here, which is a good sign. And of course, there is a common factor. Now, the original problem did not have the greatest common factor listed. It was just a common factor. And since 5 is common to both 60 and 50, and m is common to m to the 4th and m squared, we can factor out 5m, again, even though it's not the greatest common factor. And we're left with 12m cubed minus 10m. And now we certainly have an expression that we finished with that matches precisely what we started with. And that's a good result for number 28. Let's try two more to wrap up this video. We'll do number 38 and number 41. And these indefinite integrals do involve trigonometric functions, so I think we'll be referencing the rules that I had in the notes from the last video. With number 48, we're being asked to find the antiderivative, or the indefinite integral, of sine of 4t minus sine of t over 4. So what I'm going to do first is split this into two integrals. So we've got the antiderivative of sine of 4t with respect to t minus the integral of sine of, and I'm going to write this as 1/4 t dt. I'm doing this because it follows more closely to the format of the antiderivative or indefinite integral rules from the last video. Now it looks to me like we're using this rule twice, where a is identified as the multiplier, constant multiplier inside of our grouping symbol. And when we use that rule, the antiderivative of sine is negative cosine, and when we have this multiplier on the inside, what we want is a negative 1 over that a value. Now this a value is 4, so we'll call this 1 over 4 cosine of 4t. And we could add c here, but I'll wait to the end to include that plus c. Now we'll subtract. Now this is where it gets a little bit interesting. We want a negative 1 over a. Well, a is 1/4 here, so negative 1 over 1/4 cosine of 1/4 t, and we have this plus c to tack on at the very end. We can, of course, clean this up a little bit. So negative 1/4 cosine 4t, I think that's fine the way it is. But now I have a negative symbol in front of this grouping symbol and another one on the interior, so those two are going to distribute in and cancel out. And 1 divided by 1/4 is 4, so we'll finish this with plus 4 cosine of t over 4 plus c. And to me, that looks like a pretty good antiderivative using the rules that were established prior. To check, of course, we will take the derivative of this result. So the derivative with respect to t, I'm going to push this 1/4 to the front as a constant multiplier. The derivative of cosine is negative sine of 4t. Because of the chain rule that's necessary here, I do have to multiply by the derivative of the interior immediately. And in our second group, the derivative of cosine is again negative sine. Keep the interior as it is, and then multiply by the derivative of the interior. The derivative of c is 0. And we can simplify this result. Negative 1/4 times 4 is negative 1. Negative 1 times negative sine is positive sine of 4t. And 4 times 1/4 is 1, times this minus sign, of course, is negative 1. So we now have negative sine of t over 4 and plus 0 at the very end. So the derivative of the answer that we thought we had ends up being sine of 4t minus sine of t over 4, which is the same as what we started with. And now we've checked our work, and we're in good shape. Now I'm recording this video right before school starts, so the bell's about to ring. You may hear it in the video, or I may edit it out. But let's go ahead and finish up this last example, number 41. In number 41, we're being asked to find the antiderivative of secant squared of theta plus secant theta times tangent theta with respect to theta. And at first glance, this may look awfully intimidating and or challenging, but I don't think you have to be too concerned, because when we consult our antiderivative rules from the last set of notes, so here we are at the very bottom here, we actually have a set that accounts for both of these. The secant squared of theta is this guy here. Now, our theta value, our independent variable, whoops, wrong screen. The independent variable here is just theta. There's no coefficient in front of it, or technically there's a coefficient of 1, so we can treat this as an a value of 1. And same thing with secant times tangent. Secant times tangent, well, that's this guy here. That's the antiderivative. I'm sorry, the secant tangent is the derivative of secant itself, so the antiderivative of secant tangent is secant, again with an a value of 1. So if we split this into two antiderivatives, we can account for both of those individually, and we'll go ahead and do this kind of in one step. The antiderivative of secant squared is just tangent, so we'll call this guy tangent of theta. And if you really wanted to follow the outline of the notes that were given to you, you would have 1 over 1 times tangent of 1 theta, because our a value is implied to be 1 right here. Similarly, the antiderivative of secant times tangent is simply secant of our angle measure. Again, we can think of the a value as 1, so we can say 1 over 1 in each of these cases. Oops, sorry, on the interior here, that's just a times theta, so 1 times theta. But clearly, 1 divided by 1 is 1. 1 times theta is theta, so I like tangent theta plus secant theta plus c as our antiderivative. And if we were to compute the derivative of tangent theta plus secant theta plus c, and you may have to consult your derivative rules for this one since it's been a while since we've seen them, but the derivative of tangent is secant squared theta. The derivative of secant is secant theta times tangent theta, and the derivative of c is 0. And so the result after computing the derivative of our suspected answer is indeed the exact same argument that the problem started with, so we're in good shape. So I hope this video helps clarify some things and gives you perspective on computing antiderivatives or indefinite integrals on your own. If you've got further questions, by all means send me a message or ask me in class and we'll try to chat about them. And of course, you can always use Math Excel for additional help, even if the problems themselves that I've assigned don't show up in your Math Excel assignments. Thanks for watching.